hear me, that you see me. Hi everybody, I expect some symbol in chat just to prove that you can hear me, that you see me. Yes, okay. So we are starting our short mini course on verification on blockchain, and today is the first lecture. And yes, it's translated via YouTube, and you should be able to ask questions and maybe write some comments, and I'll definitely try to answer. And okay, let's start. And I will really appreciate any feedback and your involvement. So let me push the right button, this one. And now I believe that you should see my slides. Right. Okay, so the title of our course is Verification of Smart Contracts on the Ethereum blockchain. And probably the primary goal for you is that at the end of this course, you at least understand every single word in this title. What's blockchain? What is it? Ethereum? What's contract? Smart contract? And what's verification? And okay, our first lecture will be focused on formal verification. Okay, and this is the plan of our course. So you see, we have in mind to organize 7 events. Out of them, 3 are lectures. The first will be today. It's on formal verification. The second will be the day after tomorrow, on Friday, and it will be focused on blockchain, on Ethereum, on decentralized finance. And the third lecture, final third lecture, will be in a week on Monday, 18th of April. And at this lecture, we'll just combine all knowledge we'll have about the time, combine the ideas of verification with the knowledge of solidity of blockchain to see how these methods and techniques work for particular applications. And for every lecture, we have also planned some kind of seminar or question and answer session. And you see they're scheduled for the next week. And another one is for 19th of April. And right, first of all, we expect some feedback, some questions from you. So we'll be happy to answer on them. But besides, we already scheduled some maybe workshop or online session which will be focused more on practical applications, maybe some examples. And okay, they are in gray. So, and currently we hope to have offline section on 21st of April, but okay, just follow the announcement. We still haven't decided finally about the location, but I hope we'll be able to meet here in Colombo, Sri Lanka, just to discuss the future development of this topic and possible maybe projects. And I hope to see everyone who will be able to come here. Okay, and the plan for today's lecture is, okay, a lot of buzzwords, probably some mathematics and maybe not simple stuff about formal proofs, about Hoare logic, about formal verification, the safety critical systems, and we'll conclude with applications in particular with Microsoft Z3 theorem prover. And okay, this picture is more about motivation. Why do you really need to know all this formal logic and mathematical stuff? And the analogy for me is like a combustion engine is for your fancy sport car. So assume you would like to drive a nice car. Definitely, there is no need to be an expert professional engineer in combustion engines. So if you don't understand every detail and every part of its picture, it doesn't mean you can drive this car. But at some point, it's really useful to at least understand the basic idea, the basic structure, construction, some nice features of implementation, just to understand better how your car works. And that's exactly the idea of today's lecture. The axiomatic method we'll speak about is kind of an internal part of every formal verification tool, which is you don't really have to understand every detail about axiomatic method and proof engine, but to have just a general picture, some basic ideas of what's about is really useful. So don't afraid if you don't understand everything. That's okay. No one understands everything. And to be honest, it probably would take maybe 1 year or even more just to go deeper into these details to really become an expert in this profession, in this topic. So definitely it's not possible to cover everything in 2 or 3 lectures. But today's my goal is just to give you some basic ideas so that you understand how this engine works, so that you will get better idea of what's possible in formal verification, what's not. Okay, I hope you will see. So the first section of my lecture is about reasoning about infinity. So our course is closely related to what our company does. It's basically about testing, about quality assurance, about quality of complex software systems. And this is a simple example. Consider, you see the first line, you have some kind of, system under test, which has to kind of, and you need to check some property, like if it's always you have some kind of invariant, like x plus 1 times x minus 1 always equals to x squared minus 1. So typical task for a tester. So you just try to study the domain to understand better what's about, and then you come with some really nice tests, like, okay, you have some positive number, negative number, 0, non-zero, small or big, and you may create like 10 tests, maybe 100 tests. Then some of you probably are good in automation testing. Then you can just write a script which generates maybe 1 billion tests. But okay, what's good about testing? You can always do that. But what's not good, even if 1 billion of tests are kind of okay, that never guarantee you that your system is 100% correct, right? Because it always may happen that some particular instance of some particular input may result in system crash or some incorrect behavior. So, and the main issue is infinity, right? Because if you are speaking about integer numbers, there are potentially infinitely many integer, and it's not about resource. You may have all the resources on the earth, but still that's not enough for infinity, right? So what to do? And mathematicians already know what to do in this situation. Instead of testing, you should apply formal reasoning. And this is well known for maybe centuries already in science. It's called the axiomatic method. So instead of testing some particular inputs and outputs of the system, you just start from some basic properties which are kind of self-evident, like you see line number 1, a b plus c equals always a b plus ac. So it's so simple that you can assume it's like always correct. Then commutative property is even simpler. That clearly, if you take 2 numbers, you add one another, then probably the order doesn't matter. So usually axioms, they just formalize some very basic, very simple properties of your domain. So like from items from 1 to 5 look like evident for everyone, and I assume that no one would disagree that they're correct. And then starting from these properties, you try to go step by step to derive what you really need, right? And then you see line number 6. And in fact, line number 6 is just an instance of line number 1, right? And then at some point we had to just change the order. So immediately from 1 and 2, you get the 6, right? So that should be quite straightforward, right? Then once you have 6, then number 7 again. You just apply 1 and then you get 7, right? Then you start from 6 and then apply 4 and 5 and you get number 8. Okay, maybe no need now just to go into details. You will have more time with my slides at home to check that everything is very simple, is very straightforward. And finally, step by step, you just get line number 9, which is exactly, you see, what we need to get. So the idea is that instead of testing particular inputs and particular values of inputs and outputs, we just start from basic axioms and we step by step derive some properties which are universally valid, which are kind of always true. And since we started from very basics at step 9, we could be sure that this is always true for all possible values of x, right? So that's basically the idea of axiomatic method. So, and usually when you apply axiomatic method, you have like 2 parts. You see, the first part is about domain axioms. So before applying axiomatic method, you need to go deep and study your domain, your application area, and explicitly formulate all these axioms and truism, postulates, basic rules, which are true and always correct in your domain. That's the first part. And then the second part, you start from the basic truths, from axioms, and you derive what you call theorems, conclusions, statements, assertions, claims, which you can then assume as being always correct in this domain, because they are immediately follow from some axioms and using some trivial rules of inference. Okay, this basically the idea. And if you compare pros and cons of testing and formal verification, we can see that for some cases testing is much better, and in other situations formal verification has its advantages. And okay, let's go line by line. So the first line is mostly about resource. Assume we have like not much resource, like okay, $100 doesn't matter. Even for very small amount of budget which you have in your project, you can always use it for testing. Okay, you have resources just for 1 man hour. Okay, spend this 1 man hour by testing. At least you will get some information about the system, right? That it doesn't crash. You have more money. It's okay. You can spend maybe a couple of days or hire a couple of people and go more deeply into the system. So the first advantage of this is it's a kind of simple, straightforward. So, but for formal verification, it's not the case. Okay, you have seen it already, and you will see it in future that it's really much more difficult. So if you don't have like a couple of weeks, you would better not start, because you will not finish even a simple conclusion. Then all you have done would be like kind of in vain. So without like a sufficient number of resources allocated to this project, you probably should not start. The second line is about employees. And again, testing in this sense is better. Even if you have kind of junior, very unexperienced staff who just enthusiastic but don't have much knowledge, you still can involve those people into testing of your system. Okay, just provide them with very simple instructions. Just okay, take this input, take this output, check whether they're equal, and you already can make something useful, provide some value to developers by informing them about the system quality. For formal verification, it's not the case. You really need some people who at least understand. Okay, so it's not for juniors. Sorry. Okay, then the third line is more about kind of prerequisites. So before you start formal verification of your system, you really need some formalization. what I already said before, you will have to provide all these formal axioms and postulates about your domain, or hire someone to analyze that. Before you have all the list of the axioms about your domain, there is no sense to start verification. But for testing, there are kind of no prerequisites. Your system could be not very good specified, not specified at all. It could be incomplete with some kind of partially already developed in some intermediate stage of maturity level. Anyway, you can test it. You can get some useful information. So testing is applicable. Formal verification is not. But on the other hand, there are some advantages. First, what I already mentioned, testing is never complete. But formal verification is. So at some point, once you derive some conclusion, you can be sure that that's okay, that it's always true. And the second, testing, okay, sometimes it's reusable, at least test cases are reusable, but information about system behavior when system have changed, it even slightly changed, is useless. So if it was yesterday and developers introduced some new feature, you can forget about it and you need to start testing from the scratch, because everyone knows what's regression bugs, and some new feature usually means some new behavior. And one system is evolving, each time you need to start testing from the scratch. But for formal verification, it's not the case. Formal verification is highly reusable. Like I mentioned, the first stage of formal verification, you need to explicitly formalize the domain. And once you did that, you can reuse it for all possible versions and all possible implementation of the system, because the domain usually is assumed to be fixed. So all the axioms are the same, the postulates are the same, the rules are the same. And once you proved something, like ancient Greek Pythagoras proved that in every triangle some property holds, like 1,000 years after, you still rely on this property because it's still valid, because, okay, geometry is the same and properties are the same. So although it probably was much more difficult, required much more knowledgeable team and additional work, once you get this proved, you can use it like forever, and really forever. So that's kind of about positives. And okay, negative, we already mentioned. So contrary to testing, formal verification is difficult and requires knowledgeable team and requires domain formalization, but testing on its side is not perfect either, because it's never complete and hardly usable. That's end of our first section. I would appreciate maybe some questions. Do you have some comments, at least some smiley that everything's okay? So, okay. So that was general idea of axiomatic approach. And now we are trying to apply this axiomatic approach to software. And like I mentioned before, applying this to a particular domain would require two parts. First, you need to define all possible axioms, and then you need to derive some tools to derive theorems, conclusions, and statements. And this is how typical statement about software looks like. And it's called Hoare triple. And it describes how the execution of code change the state of computation. So think, so this think as computation is just a sequence of states, where system state is just usually a snapshot of values of all possible variables and fields. So we start from some system state, then you run your code, and the system state is changed. Like in simple situation, you just update one variable, But for example, for transactions, you need to update in parallel like couple variables, and because partially executed transaction doesn't make sense. So the code could be either simple, either more complicated, but anyway, the piece of code after you execute it, it changes the system state. So the idea of this triple is it says the following, that once we had some property before the executing of the program, and we know that this particular code is executed, then one could be sure that this post condition, this property after, I mean, the property of the system state, the property of the variables and objects that, and whatever, and stacks, whatever data type we have, this property will hold. So the property before the system execution is called precondition. The property which we expect to hold after the system, the code execution, it's called postcondition. So, okay, that could be slightly unexpected, but let's see the previous example. So you see that although mathematics is could be sometimes quite complicated, but usually in mathematics we have only two types of statement. The first type is implication. You see, if something happens, then something else should happen. You see, it's like line number 3, number 4 here. So if A equals B and B equals C, then A equals C, right? And the other type is just equality. You say that something, we have left hand part of the equation and right hand part of the equation. And then every transition just teach us how to transform this equation in the way that it still kind of remains equivalent. So in mathematics, we work with equations and with implications. But in computer science, we work with triples because we are interested in what was true before our program, kind of preconditions, some requirements, or some maybe constraints of our input values. For example, you have some, for those who are developers, it's completely clear that not every method could be applied on every data value, right? So you have some restrictions which you expect to be valid, and usually we put them into precondition. So once precondition holds, you apply your code, then you can be sure that postcondition holds. And here are the axioms of this Hoare logic. They are very few. And it's quite clear that for every statement in your programming language, you can define something like that. So in fact, axioms are exactly the basic properties of your programming code. Okay, there are a lot of Greek letters and fancy structures here. So surely this is a good topic for research, for PhD, and a lot of maybe hundreds of thousands of PhD will defend on this topic. But like I mentioned, you with picture of Tim and John, you don't have to understand everything. So because it's really sometimes quite advanced and requires quite serious mathematics. But my goal today was just to show you the basic idea. So at this point, I'll finish with mathematics. So that's the most difficult, the most serious mathematical slide. If you're interested, you can find a lot of literature, maybe video and courses on this topic on the web. But just to conclude this section of my lecture, I would like to mention, I already mentioned that this is called Hoare logic. And Hoare is a very well-known British computer scientist who contributed to very different areas of computer science, including algorithm and distributed systems. And most of his life he spent in UK working at Oxford. But while preparing this lecture, I realized that he was born in Colombo, in Sri Lanka. So we are here at the right place to speak about verification, because Tony Hoare, who is really the father of all this stuff, was born here. And you see his mother was the daughter of a tea planter here. So he's really Sri Lanka guy. And I really feel proud to be here for this lecture. Okay, so let's go to the next section of my lecture. And right, this is quite short section. It's about safety critical systems. That's really important when you try to study something new in software engineering, computer science, some new tool, some new computer language, maybe some framework. You really need to understand first the focus area of application for this, because before that you might feel like okay, some strange technique, some strange tool which no one will probably use. And the same here. So once you look at these axioms and rules of inference, the first impression, wow, that's probably really difficult. That's really very costly and time consuming and requires really strong team, and probably no one in the software engineer world would use it. And in general, you are kind of 95% right, but there are some examples, and they are listed here, when the development team, the owner, the project owner, they don't really care about cost and time, because their systems are related to safety, to some life critical applications, maybe to human life, etc. So there is quite many. Okay, that's not a kind of everyday examples in your life, but there are quite many examples of software and hardware systems where you would be happy to spend even maybe more money and time if it really guarantees you more additional quality, like higher level of confidence, etc. So, and you see on this list that the systems are related to some medical applications, maybe traffic and railway and flight traffic and nuclear stations, and because this system is not really huge, and the cost of project is really huge. So building a nuclear reactor would cost not $100. So spending another piece of money, another piece of time, just to ensure that your control system is really safe and correct, it's okay for these people. And that's exactly where formal verification is very well known, is widely applied, and it probably started like maybe 10, 20 years ago already. So it's kind of, they don't consider it like something fancy and a strange technique. For them, for people who work in these areas, formal verification is like daily business. So at this point, I'm ready to show you the formal definition. And it says that formal verification is the act of proving or disproving the correctness of intended algorithm underlying the system with respect to certain formal specification or property using formal methods or mathematics. So let's go line by line, but probably from the end. So you already see that this technique is using formal methods of mathematics. And this is already clear, I assume, right? Yes, and any questions and comments are welcome. Yes. So let's see the line last but one. With respect to a certain formal specification property. This is very important because for testing, you really can start testing system without specification, because at least you can run smoke test, you can check whether it crashed or not, you can collect some information for which inputs, what's happening, you can do some non-functional testing. So formal verification, not formal, just specification is desirable for testing, but not really necessary. For formal verification, you can start until you have formal specification, because you can always you need to prove some property finally, but if you don't have this property to prove, you can do nothing. So what's really important for formal verification is you always work with specification, and that's another kind of issue of formal approach. If something is not specified, you can't verify it. And this, incomplete specification is quite usual situation, and that could be an important issue. For example, you develop some control system for nuclear reactor, and you listed all possible risks and then you prove that these risks are not can happen with your system, but still it might happen there is some unknown risk which is not included in the specification, then you can prove it. So you should avoid this kind of false feeling of confidence. So because formal verification is okay, but still you might have this human factor, so it could be incomplete. Then let's see the second line of intended algorithm underlying the system. So that's also very important, that system quality, if you speak about overall system quality, is not about algorithm only, because algorithm is implemented in some particular language. Then you use some particular compiler to transform it to some bytecode. Then use particular hardware and infrastructure to run it. And it might happen that algorithm is okay, but for example, compiler might have some, it's quite typical situation that compilers do some optimization. And with this optimization, it may introduce some bugs. And so compilers are never perfect, and hardware is never perfect, and infrastructure is never perfect. So, and you should always have that in mind. So that verification kind of ensures you that algorithm is correct with respect to specification, but you know nothing about the infrastructure and the hardware. Okay, and the first line is more or less correct, right? Understandable, yes. The act of proving or disproving. So you start from specification and algorithm. You try to prove it, and either you succeed, like Pythagoras with his theorem, or at some point you can realize that you can prove it, and you end up with some counterexample. That's okay too. That's happened quite often, and this counterexample is usually easily converted into some test case, which shows you that the algorithm is incorrect. Okay, this is the definition. Okay, questions welcome. And let's go. Yes, and this slide is already, I already started to speak about it, that if you speak about product quality, formal verification is just one, okay, small or big, doesn't matter, but just one part of functional testing of your system. So first you should understand that quality is not only about functional properties, because sometimes you need non-functional, you need support, you need a good team, a good specification, and different factors. And even for functional testing, formal verification is just one of possible tools which can replace like a good test plan or manual automated tests, which could be run on different configurations, different hardware, etc. So it's really important to understand the role. So it's really useful. It can add value, but it can't replace all the other job which has to be done for your quality to achieve. Okay, and just to conclude this section, just a couple of benchmarks. Like I mentioned, almost 20 years ago, Intel already used formal verification for some protocols. Then you see some examples: compiler, operating system, and even blockchain. And you see this example for blockchain is already like 6 years ago. So once blockchain technology arrived on the market, people started immediately some experiments on applying formal verification to these tools. And okay, right. And truly, like I mentioned, hardware companies really like this topic a lot. And okay, that's probably okay. I see some question about how about termination about whole triples. That's a very nice question for a while, because like I mentioned, if you okay, let's open the definition. Yeah, so So the meaning, the semantics of this triple is that when the precondition is met, executing the command, and implicitly it's written here that successful termination of the code ensures the postcondition. And definitely, if this while doesn't terminate, you can write here everything you want, and it will be correct always. Termination proof is really another interesting section of formal verification. There are definitely some techniques how to prove that system terminates. And okay, there are kind of two subsections. The first, there are systems which should not terminate, like operating system or TCP/IP protocol. They're expected to run forever. And like I mentioned already, verification is already applied to operating systems and protocols. Usually you prove some kind of invariant for this kind of system. So you take some piece of this protocol and you prove that this or that invariant still holds, whether independently of which computation branch you use inside this protocol operating system. So this is one situation. And another situation is when you really need your system to terminate, and it's not clear whether it's possible, because sometimes the algorithm could be quite complicated, and in principle, it's possible to find some very specific input values and race conditions when your system goes into some kind of a circle. Then there are separate techniques how to prove the termination with something like Hoare logic. But okay, so the short answer is yes, there are techniques to deal with termination. The second is no, today we will not discuss that. Okay, thank you for the question. And let's see, maybe some other questions. So, okay, no. Okay, and the last section for my today lecture is about Microsoft Z3 prover. You know, these guys don't call it prover because okay, they prefer SMT solver. That's probably a nice topic to discuss because, you know, there are quite many tools which do kind of formal reasoning on the market. And, you know, it's kind of different design decisions. You can do this tool like more powerful, but then most probably it will be kind of more interactive because automatically it's really difficult to prove really serious theorem. So one group of tools of this type, they are usually called provers or proof checkers. They are very powerful. They kind of based on set theory or other maybe serious mathematics. They can do everything, like they can prove correctness of any protocol or operating system, but only with human involvement. So it's not automatic, and they call it provers. But Z3 is from different group, which is more focused on practical application. And, you know, in the real industry, people like one-button techniques. So they prefer not to spend much time and hire new people. They are better just to buy, maybe purchase, or maybe spend some time to maybe to study new tool. But then once this tool is incorporated into the workflow, it should work automatically. And that's how Z3 was designed. So the idea is to make it, to minimize the human involvement. And that means that in some sense, Z3 is incomplete. So if you take some serious kind of really huge system and you'd like to prove something about it, most probably Z3 is not good choice for this. But for very clear and specific applications, Z3 is okay. and it will do it in efficient, simple, and with minimal involvement of human resource. Okay, that's why the tree is very popular in industry. Okay, and right, so it's about different groups of provers or solvers, and definitely I assume, okay, at least among my friends, everyone knows about computer algebra systems, which kind of maybe 20 years on the market. So once you need to solve some equation or set of equations, you can use all these computer algebra systems, and they are in some sense from the same group, right? Like theorem provers, because they do some reasoning, they call it symbolic computation, to transform, to simplify, to solve some equation, etc. Another group of solvers are called set solvers, because they usually do with Boolean logic. And here are some links, and I plan to distribute the slides, so you can just follow the link and see the examples. So they're mostly focused on doing some logical combinations, some more maybe combinatorical stuff, some heuristics about very specific combinatorial problems. They are called set solvers. And SMT solvers, and the tree is one of them, they combine both the power of set solvers and computer algebra systems. So you can use the tree to solve equation or some inequation, but also if you have some quite complicated Boolean combination of different properties, which exactly what we have in programming language, because while, if, then, else are exactly Boolean combinations of different properties. It's exactly it's exactly the focus of SMT solvers. So it's a combination of Boolean logic with some particular theories related to computer algebra, whether it's arithmetic, some equations, some maybe other theories which describe properties of a stack, for example, or something else. Right, and here's just a short introduction. So it's a SMT solver, already described it. So you can download and install it on your computer, but also you can run it from your browser. There is quite a big community in the world of people who work with it, both in academia and industry. So there's quite many different information, useful tips and tricks on Stack Overflow. And besides kind of native use of the tree, it has very nice integration with different programming languages, especially with Python. So you could call it directly from Python, which is very nice for automation and the industrial use. So another slide, just some glory to the tree. Okay, so you see some code. So it got the award of being the most influential tool paper in the first 20 years of TACAS. It's the major conference on software engineering and computer science. So it has more than 3,000 citations. And also it's got award from ECM. And the tree, like, you see again the similarity with combustion engine. So people usually incorporate this tool inside other tools as some core part, which is already done by Microsoft in different tools like Isabelle, PEX, and Visual Studio. Also has integration with the tree. And you see some just line. The last line is that it was highly used for recent shipment of Windows 8 Office. So you see, it's a real industrial power. It's not just academic project. So the tree, it's a really industrial level powerful tool. That's why I really encourage you to spend some time on studying. Here's just a very simple example of using this tool. So that's how we ask the tree to solve some solve some equations and inequations. So although it may look some strange, but once you spend maybe a couple of minutes, you see that everything is more or less simple. So the first part is actually declaration of variables. And from point of view of mathematics, variable is just a function with no input values. So that's why instead of writing declare variables, it's written declare function, but you see parentheses are empty. So A is just, okay, you may think that it's like a function with no parameters, but actually it's the same as variable. So A, B, C are integer variables, and this is just declaration section. Then you declare these constraints. So by default, different lines mean a conjunction. So if you write something, then you some property, then on the next line you write different property. By default, it means that and. So be sure that this happened and this happened and this happened and that happened. So in this example, you have 4 different properties, and they are written in prefix notation. So you first write the name of the function. In this case, it's greater than. It's just Boolean function, which takes 2 parameters. The fourth one is equation. Again, equality is just another Boolean function which has 2 parameters. And you see this call out on the right. It's exactly what's written here. So here you see A greater than 0, and B is greater than 0, and C is greater than 0, and A square plus B square equals C square. And so you define these constraints. So all the arithmetic equation, or I mean all the arithmetic axioms are already defined in the basic library of the tree. So you don't need to formalize all this commutativity and other laws of addition multiplication. So everything is already done. So you just define the properties you need to run, and then you just call the check satisfiability function. And in the case it's satisfiable, you get the model. You ask to get the values for this combination. So that's actually all I have for today. Questions are welcome, comments too. So yes, like usual university teacher, I prefer to have home assignment. Surely you will be allowed for next lecture even if you don't do a home assignment. But for those of you who are interested just to check yourself, to maybe understand better, so it has 2 parts. So the first is theory test. It's just Google form with several questions. They are okay. As for me, they are very simple, but you can use every resource you have on the web just to answer this question. Just go one by one and just to refresh everything we discussed today. And also, you see the implication, the second task. So I assume that maybe 7th grade school student should be able to solve it, or maybe even younger. So from human point of view, that's quite simple implication to check if it's correct or not. I mean, correct for all x, y. Either it's correct for all x and y, or there is a counterexample. And the tree is exactly the tool which can do that for you. Either prove it that it always holds, or prove that it's not always hold. That means the negation of this implication is satisfiable, and then provide you with particular values of x and y for which this implication doesn't hold. So I ask you to use the tree either directly or on the web interface or from Python just to check this equation. And then I ask you to put your code onto your GitHub account, and then just paste link to this folder into the theory test. So the last question is in the theory test. I just ask you to provide a link to your Z3 task. Okay. Yes, I see some questions. Okay, while true is answered, and only surely everything I told you is just very basics of axiomatic method, very basic part of the tree. So the tool is quite has quite extensive language and features and different extensions and libraries. So surely it's much more stronger than what I just mentioned. So my goal for today was just to give you some basic idea how this proof engine works. So what's possible, what are kind of pros and cons of this approach, what's possible, what's not. And surely I suggest you to, if you find this topic interesting, just to dive in and to go to the tree webpage to see the videos and the documentation on the web to understand better the functionality and what's possible with the tree. So surely it's much more powerful than what I just mentioned to you. So wow, I see the guy who knows what's Pressburg arithmetic. Uh, uh, yes, the tree has a lot of different theories, and in addition, you can extend it with your own theories. So that's why it's called Satisfiability Modulo Theories. So it has modular architecture, so you can always add your own module for your theory with your own okay, axioms and rules and even some maybe decision algorithm too. But by default, right, it's restricted with Pressburg arithmetic. It's I mean it's addition only, right? Okay. So, okay, let's me remind you again. So that the second lecture is on Friday, and next Monday you'll have a special section related to this topic with questions, answers, and I plan to show you maybe some more running examples of the tree, and we'll just spend more time on some practice and tools. Maybe some demo and etc. So thank you, thanks everyone, and also to people who here in my room. Maybe some questions, comments. No. Okay. Thank you again.